Hello, everybody. My name is Rob Thomas. I'm the librarian at the Institution of Structural Engineers, and I do look after the institution's history study group. I'd like to welcome everybody here tonight and everybody in the Zoom audience for this joint lecture of the institution's history study group and the London branch of the Newcomen Society. Tonight's speaker is Bernard Espion from the University of Brussels, who's going to talk to us tonight about the history of Vierendeel railway bridges in Belgium and the Congo. Thank you, Bernard.
Thank you, Rob, for the introduction. Ladies and gentlemen in the room and online, thank you very much for attending this lecture. It's about the first time that I lecture here in London, either for this group or for the Newcomen Society. Always a pleasure to exchange ideas with the audience. And since you are still inviting me, you are not too much disturbed by my French accent. Sorry for that. Last time I lectured, it was in January 2019, long time ago before COVID. But I had always promised to Julia Elton that I would speak one day about Vierendeel girders. Unfortunately, Julia cannot be here tonight, and she sends her apologies. The subject of tonight will be narrow, not the whole story of the Vierendeel girders or Vierendeel bridges, but mainly concentrated on railroad bridges. So who is Vierendeel? He was born in 1852 in Leuven, an illegitimate child. He was raised in a small town in Flanders, Gerardsbergen, Gramont in French. He did engineering studies at the University of Leuven and graduated in 1874. For 9 years, he was employed by a Belgian construction steelwork company, the Atelier de la Louvière, and gained experience with steel structures, design and erection. He observed in particular that it was difficult to actually construct without stressing them, the elements of the diagonals of trussed elements, trussed girders. In 1885, he was hired as an engineer-in-chief, director of the technical services of the West Flanders province along the coast, the Belgian coast. That's an official position, but not a state official position. It's a provincial one. He enjoyed much freedom for his decisions there, and he lived in Bruges. In 1889, he was designed as professor of civil engineering at Leuven University, but at that time, he had only published in 1886 only one paper on design of springs. So he was not known for theoretical achievements. He kept both positions in parallels for decades. And I should add a third occupation from 1896 and the submission of the patent of the girder that made him famous. He embarked in a position of patent holder, aggressive promoter and defender of his patents, and consulting engineer, himself designing or supervising the design of many bridges according to his system. So at the time of the submission of his patent, he was already 45 years old. And I would say that he was typically a 19th century man and a steel engineer. So I guess that you know that the so-called invention of Vierendeel was to remove the diagonal elements of the girders. At the time when the standard design of steel girders were either lattice or worm type. This is a typical railway girder produced by the Belgian steelwork industry around that time. It's a 150-meter span for the railway line between Matadi at the mouth of the river Congo and Leopoldville, then the capital of the Congo, completed in 1898. He exposed his idea in a paper published in 1896 in Belgium, and also in patents submitted in Belgium, in Great Britain, in Austria, and in France in 1896. The text of the 3 patents shown here, the Belgian, the UK one, and the French one, is very similar. Was better on my screen, sorry. Here are the plates of the patents that illustrate this idea of girders without diagonals. We have rather sturdy and stiff nodes, and also vertical posts, here or here, with significant bending stiffness. Vierendeel imagines girders with constant depth or slightly varying depth above here. Of course, this strange design with double level of cells has never been applied, and neither has ever been applied this fancy, let's say, neo-Gothic architect deco of these bridges. Was the idea of removing the diagonals really new? Quite certainly not. The story of the girders without diagonals before Vierendeel has to be written. I have picked here 2 examples in the UK, well before 1896. They are both quoted in the book by Renison on North-East Civil Engineering Heritage. There is this large railway bridge over the Wye River in River in Sunderland, built in 1879, still in service, and the supporting girders of the canopies and the roof at Durham Station from 1870. To be fair, Renison does not state explicitly that these are actually true Vierendeel structures. Typically for the arch bridge, he says that it is a Vierendeel bowstring type. And I suspect that the actual structural behavior is more of the bowstring type. And the Durham girders, being in cast iron, could never actually function safely as Vierendeel girders. Removing the diagonals of a girder is not sufficient to have the structures truly working as a Vierendeel girder. Why? Here we have to hear the arguments of Vierendeel and understand the context of structural design at the time in the mid-1890s. Vierendeel was well aware from his experience, as many other engineers, that the elements of a so-called trussed girder are submitted not only to normal forces, but also to bending. This bending arrives from the practical realization of the connecting nodes made with gusset plates and rivets, which are not perfect hinges. So the stress arising from the rotation of the nodes, and therefore from the bending of the elements, were called secondary stresses, although they were known to be not so secondary to the primary stresses resulting from the normal forces. So there were already methods available to estimate these secondary stresses, but they were very tedious and cumbersome to apply. The practice and the philosophy of design of truss girder and the girders at the time was: one, assume all nodes to be fully hinged perfectly. Second, derive the normal forces in the element only by the equation of statics, of equilibrium, or by graphostatics methods. Then ignore the secondary stresses, apply the admissible stress design approach by assuming an allowable tensile stress of about 120 MPa in modern terms. And then check the elements in compression for buckling. And I should add that of course, at that time, the buckling formulae were far from being accurate. So Vierendeel raised, quite rightfully, the validity of such an approach. What's the meaning of safety in such a design approach if the analysis forgets stresses which may amount up to 100% of the primary stresses? Of course, we have to remind that the assumption of linear elastic behavior was paramount at the time, and that nobody spoke, or at least wrote, about plastic adaptation. The position of Vierendeel was remove the diagonals, assume full frame behavior in all elements. That's the second illustration here, which are then submitted to normal force and bending, and also shear, of course, and account for all stresses. Fine. But this implies a change of paradigm. Even for a simply supported girder, from statically determinate truss to statically indeterminate frame with moving nodes. And at that time, still for decades, the detailed structural analysis of such girders remained extremely difficult and time-consuming before the advent of computers. And at that time, of course, the Vierendeel girder was somehow in that form out of fashion. Vierendeel proposed his own method, which simplified assumptions. I do not go into the details. Already in 1896, and during decades, there was a debate between academic researchers and practicing engineers about the best method to analyze Vierendeel girders. I will not venture into that review because this would be the subject of another full lecture. Anyway, Vierendeel could therefore claim that his girder and method were more philosophically truthful than the trussed hinged girders with triangles. But he also claimed that his girder was more economical. This is very dubious. He only could reach that conclusion at the time considering the costs of construction versus the cost of materials, and by adopting a higher allowable stress for the steel, 140 MPa instead of 120. And he justified that by saying that his method of design included all stresses. The third advantage claimed by Vierendeel for his girder without diagonals was that it was more pleasant looking and enjoyable for people traveling in coaches across railway bridges. That's a correct argument also. From the very beginning, Vierendeel envisioned the railway bridges as the main market for his girder. And here you can see an illustration for a prototype of a single track girder with a 41.5 meter span. And the following year, 1897, Vierendeel set up a test up to failure of such a prototype. Exactly. This occurred during the international exhibition held in Brussels that year. It is said that Vierendeel paid himself for the test. It took place in Tervuren, in Brussels, on the grounds of the site of the exhibition dedicated to the Congo. Anyway, this is an extraordinary test by its sheer size. The loading of bridges were common, but I believe that there had never been before a test up to failure of such a large steel girder for bridges. The Ministry of Public Works dispatched 2 engineers to watch the test. They wrote an extensive report which raised doubts about the claim by Vierendeel of the economical character of his system. Vierendeel immediately replied and dismissed the objection of his contradictors. And this will always be the same trend for decades. In the discussions concerning his system, Vierendeel praises the engineers who support him and attacks vehemently and often with bad faith the detractors of his system. He never accepted any criticism of his invention. 3 last comments here. One of the 2 witnessing engineers and author of the report was Paul Christophe, who will be 2 years later the first to publish an extensive and non-commercial survey of the state of reinforced concrete construction and technique, and also to introduce the standard elastic method of determination of the longitudinal reinforcement in cross-section of beams in reinforced concrete. The 2 witnessing engineers, Lambin and Christophe, published their report in the official journal of the Ministry of Public Works, the Annals of Public Works, but also the same year in the Bulletin of the International Association of Railways, which support the argument that the Vierendeel girder was from the beginnings meant to be used for railway bridges. And last remark, it's quite obvious from this state of the bridge at failure that the failure does not result from bending, but from a combination of shear and web buckling. And of course, the design concentrated on the limitation of normal stresses and completely ignored the actual failure modes. Just 1 month after the completion of the test, Vierendeel submitted his patent in the US. It includes an illustration of a different kind of girder intended for railway spans. Also, you see clearly the tracks here, the longitudinal beam supporting the tracks with varying depth at this time. But there will be no application of Vierendeel girders to railway bridges before the 1920s, meaning 25 years later than the patent. In fact, all Vierendeel girders designed by Vierendeel himself in Belgium, and there are not many, just 6 or 7 before 1914, are footbridges or road bridges. The first, top left here, in 1898, is a footbridge built in the small town where Vierendeel grew up, was raised, Gerardsbergen. Curiously, Vierendeel never claimed in his writings to be the author of that first. after the test, but it is obvious for several reasons that I cannot detail here. The bridges at Avelgem here, 1904, generally considered to be the first true Vierendeel bridge, and that one in Usselgem were built on provincial roads in the province where Vierendeel was engineer-in-chief. So he had the freedom to choose himself the system to bridge these streams and, of course, to enjoy the royalties from the use of his patent. All the road bridges before 1914 were destroyed during the war and rebuilt identical in 1918, then destroyed again in 1940. None of them subsist. Vierendeel also patented his girder without diagonals for reinforced concrete. And he designed himself this footbridge across the tracks at over the tracks at La Louvière railway station, built in 1913. In Belgium, this was the first Vierendeel in reinforced concrete, and also the first time that the arch form was with parabolic upper chord was built. I think that's a quite elegant design for the time, especially the detailed design of the connecting nodes. So the first railway bridge that Vierendeel was able to be adopted by the Belgian railways was only built in 1922. A single track bridge spanning 56 meters over the Leie River near Deins, not far from Ghent. But this bridge had a complicated history. First, I would like to remind you some dates. During the First World War, the Germans were not able to fully occupy the Belgian territory. The front line stabilized along the Isère River, and behind this front line, the territory remained under Allied control. In 1939, France and Great Britain were at war with Germany from September 1, 1939. But Belgium was only invaded by the Germans on May 8, 1940. And the battle lasted till during 18 days, till the capitulation of the Belgian army on May 28, by order of the king. In order to slow the invasion by the Germans, the Belgian army, retreating, destroyed many bridges in Belgium, and in particular this original bridge on May 25. But 2 years later, in 1942, the German army or German engineers had already reconstructed the bridge and already doubled it, because it was an important line to bring the material for the construction of the Atlantic Wall. But in 1945, this time the retreating German soldiers destroyed the bridge. That's the state pictured here on this slide. 1945, both spans were reconstructed. Around 1992, the state railways wanted to get rid of these spans, but they were preserved and finally renovated in here since 2001. Okay. The next chapter of the story of the Vierendeel railway bridge takes place in the Congo. Famously, the explorer Henry Stanley, exploring the territory for the Belgian King Leopold II, declared, "Without the railroad, the Congo is not worth a penny." I already mentioned it, a bridge built in 1898 for that line here between Matadi and Leopoldville. Early during the exploration of the territory, the mineral richnesses of Katanga had been discovered already in 1893. Katanga is this region here, north of Rhodesia, former Rhodesia. And in 1906, Leopold II set up 3 companies to exploit the Katanga province, which was still very isolated in the early 1920s. One of the problems was, of course, access. That's the reason why a railway company called BCK was set up in 1906. BCK somehow means a railway company from the lower Congo, that region, to the Katanga. In the early 1920s, the head of civil engineering department of the BCK in Brussels was Paul Gillet, here a picture, but from the 1950s. He had graduated from Leuven University and was therefore a former student of Vierendeel. From his time as a student, he had not a particular fond memory of the Vierendeel girder, that he regards simply as a favorite question exam by Vierendeel. But when he was confronted with the harsh conditions for building bridges with steelwork prefabricated overseas in Belgium, shipped and unloaded many times and erected by a poorly qualified workforce, Gillet discovered that the Vierendeel bridge was far more robust and required far less care and maintenance than the more usual trussed types. And he decides that all spans above 30 meters would be of the Vierendeel type, and 24 were built for the bridges of the line here, built between 1933 and 48, between Port-Franqui here and Bukama here. That's a 700 miles long line, about 1,100 kilometers. The most difficult bridge to build was for the crossing of the river Lualaba at Bukama, at the most western end of the line. Eastern end of the line. The site conditions were difficult for building the foundations of the piers, geological conditions, speed of the stream of the river and its flow. The superstructure of this 250-meter long bridge consists of 4 identical spans, trapezoidal in shape, of 62-meter span. The line was inaugurated on July 7, 1928 by the King Albert I and his wife Queen Elizabeth. This bridge is still standing today, even if it does not accommodate an important railway traffic. It serves as a crossing of the river for pedestrians. The bridge at Bukama may be the longest on the line, but this bridge here over the Bushimai River has the largest span, 72 meters, single track, and is of the arched type. What's typical of the Vierendeel girder can be seen quite well here, that all elements have a eye-shaped cross-section able to sustain bending forces, bending moments. And I managed to find the drawings, blueprints of this bridge in the archives of the steelwork contracting company Baume et Marpand. And what is very interesting to notice, it's written here, maybe you could not read it, so I will say it. All the technical details of the execution drawings are to be approved by Mr. Vierendeel. And you see here his signature here, dated from the last day of the year 1926. So Vierendeel probably did not himself did probably not himself all the detailed calculations of that bridge. Remember, he was also an official and also a professor at the university. But he checked the final results and signed the drawings, taking the responsibility and most probably justifying like this the fees he was paid for, either as royalties of his patents or simply as consulting engineers. Besides the Bucama Bridge, the Vierendeel Bridge built by the BCK company are very poorly documented. Apparently, there was a standard type for 42 meters span, and several were built by different steelwork shops in Belgium. With the help of Google Earth, I have spotted several of these Vierendeel bridges built for the BCK in the 1920s. They are still in place, crossing streams in very remote areas. And the definition of Google Earth is not very good for that part of the world. And they are nearly 100 years old. I have even found pictures from 2 years ago showing some maintenance. From some pictures that are kept at the Africa Museum in Tervuren, it seems that Vierendeel bridges were built after 1928 on extensions of the line. Return in Belgium, just after completion of the construction of the large number of spans, at least 25 in Congo. The second Vierendeel railway bridge, built for the Belgian railways, is for this crossing in Brussels of the canal, a shape that reminds the prototype tested in 1897. The span of the prototype was 31.5 and it is now only 39. In fact, these are two independent single track girders. They are skew also. And here also, but here on the right, the signature of Vierendeel. On the drawings, most probably prepared by the engineering office of the railways. The bridge was damaged, as many other, in May 1940. I will come back later on that kind of fracture caused by the blasts of the explosives, but it was repaired and it's still in service. The third and last railway bridge in Belgium, effectively designed under the principles and details imposed by Vierendeel is this 3 tracks bridge crossing the river Ourthe near Liège on the important line from Liège to Aachen in Germany. And once again, you see the signature of Vierendeel here. I have not found that this bridge was damaged during the war and it is still in service. In fact, it was no need to blast it before, because just another one on the same line had already been blasted. From the late 1920s, only Vierendeel, so-called tip 5 or arched form, will be designed and built in Belgium. And a significant number of these bridges will be built in the 1930s, either as road bridges or railway bridges. But a significant event took place in 1932 or 1933 to allow this. It was a settlement between Vierendeel and the Belgian government to allow the use by the state administrations, the use of the Vierendeel girder type without the supervision of Vierendeel and presumably the payment of fees to him. I rapidly survey here the story of the Vierendeel road bridges. I say rapidly because I would rather use another hour to develop this. And besides, I have already written papers about that story. This is intimately linked to the introduction in Belgium of the realization of the connections in steel structure by electrical arc welding, a novel, untried technique at the time. So this is the story of the construction of the bridge crossings over the Canal Albert, a connection between Liège and the Meuse River to Antwerp on the Scheldt River, about 100 kilometers, which was carried out in the 1930s. The first Vierendeel, and first welded, although only partially welded, was for this bridge at Lannay in 1932. And the initial design, fully riveted, had still been entrusted to the supervision of Vierendeel before the agreement. But the proposition to realize the connection by welding came from the contracting steelwork, and it was accepted because it was cheaper due to the savings in steel. After that initial success, about 50 Vierendeel welded road bridges were built between 1932 and 1937 by 12 different steelworks contractors. These are advertisements by 8 of them, and they all featured their involvement in the Vierendeel bridges of the Albert Canal. And there were 3 suppliers of electrodes or welding processes, but the leader was the company Arcos, which claims to have contributed to the welding of 50 bridges of the Albert Canal. The longest span and one of the last to be built in that series was in 1937, the bridge at Accourt near Liège. The notorious bridge at Hasselt was the longest span of the type when completed in 1936. But the bridge at Hasselt is unfortunately famously known internationally for its spectacular failure on March 14, 1938, when it suddenly broke and fell into the canal. It was early in the morning, no loads, no variable loads on the bridge, and no casualties. This is usually referred to as the starting event of the brittle fracture story of welded steel structures. But for months, even years, nobody was able to provide an explanation for this spectacular failure. And in March 1938, all the Vierendeel welded road bridges in that program had already been built. But the Hassel Bridge was not the only one. During the very cold month of January 1940, 3 other welded Vierendeel bridges exhibited significant brittle cracking. There was this small one at Colil, built in 1935. This one with spectacular crack here across the beams here and here also, at Herentals-Uhlen, and also the third one at Ermal here, also with spectacular brittle cracks. But these were only the 4 most spectacular failures. In fact, cracking in the workshops and out on site had already been observed since the very beginnings of the introduction of the new technique since 1933. And not only on Vierendeel bridges, but also on other type of bridges and even on lock gates. Conclusively, it may be said that the carrying capacity of all these bridges was clearly insufficient, considering their state, and it is somehow fortunate that they all have been blown up by the Belgian army in a hopeless attempt to slow the invasion by the German troops in May 1940, 5 months later. Therefore, the use of electrical arc welding was stopped for several years for bridge building in Belgium. And the reconstruction of the Hassel Bridge during the war, of course, resorted to traditional riveted connections. I believe that the wide-ranging applications of Vierendeel bridges in Belgium and in Congo in the 1920s and 1930s can hardly be grasped without an analysis of a network of influences between engineers. Because the Vierendeel type bridge was never extensively used elsewhere. Of course, the top influencer, as we would call him today, was Arthur Vierendeel himself, but his alumni from Leuven included a large and influential group of followers who liked him, to use the vocabulary of today. We have already seen the roles played by Paul Gillet, graduate from Leuven, in promoting the use of the Vierendeel bridge in Congo. In Belgium, we have Vierendeel bridges built by 2 different administrations, the road bridges by the Ministry of Public Works and the rail bridges by the National Railway Company. And here we have to distinguish between the engineers turned politicians who take the policy decisions. They are the policy makers. They were all former graduates of Leuven and former students of Vierendeel. And the heads of the engineering offices in charge of carrying the decisions into projects. And these were former graduates of Kent University. At the Ministry of Public Works, Georges de Kuyper here was head of the Bureau of Bridges and managed daily the design of bridges, preparing the documents for the call for tenders for the Albert Canal. But his superior was here Eugène de Brabander, who clearly promoted the use of Vierendeel bridges and advocated the use of the experimental new technique of electrical arc welding It rapidly appeared that he had a conflict of interest because his son was working for one of the steelwork contractors promoting the use of the technique, and he was sacked in 1935, which is extremely rare for an official in Belgium. Things went more smoothly at the railways company on the right. It had experimented gradually the introduction of the Vierendeel bridges on its network along other types of girders, and it never used the welding technique, only the reliable and proven riveted technique. Although the chair of the board of the National Railways since 1926, Jules Jadot was also a former pupil of Vierendeel, who certainly was keen to see the bridges of his old professor used by the Belgian railways. The head of engineering office also became convinced of the value of the Vierendeel railway bridge in its mature arch form. This head, Richard Desprez, here, was a fine engineer who wrote several scientific papers of very sound quality. He was also a professor of civil engineering and bridge engineering at the University of Brussels, where I come from, between 1926 and 1955. Now it's time to begin the story of the dissemination of the Vierendeel railway bridges in Belgium in the 1940s. The first line to be electrified in Belgium was the fast line between Brussels and Antwerp. A new line was built with two Vierendeel type bridges at Mechelen. There is this one, the largest one, and the one here on the left, on which I will concentrate a bit later. This aerial picture dates from some years ago, maybe 2 decades, because the landscape has changed somehow with the construction of a new parallel bypass here for allowing the fast train, high-speed trains to bypass the station here of Mechelen. These Vierendeel bridges here, that one and the other one, were built 1943, 34, and they still exist. So this is the largest one, 90-meter span. It's still in use, is heritage listed, has been renovated recently. These pictures, they have never been shown. They come from the archives of Desprez at the University of Brussels. Over the smallest one, over the canal, is here. But in fact, you see now 3 bridges there. This one is from 1933, 34. These 2 parallels here were built in the mid-1950s for another line. But building still Vierendeel bridges in the 1950s, that means more than nearly 60 years after the patent of 1896. These are also views of the erection of the smallest one with the span of 63.5 meters. They also come from the archives of Richard Desprez at the University of Brussels. This one, as many other bridges, was blown up by the Belgian army in its retreat in May 1940. I will come a bit later to the consequences of that later. Because quite rapidly, the bridge was repaired, and within weeks, traffic resumed on that line. The bridge was still in service recently when I visited it. Allowing high-speed trains to cross it, although at a reduced speed because of the conditions of the line, not especially because of the bridge. It was fought at that time. At the same time, two other Vierendeel railway bridges were built across the Albert Canal at Herentals. The double track span is identical to the largest span at Mechelen. There was also a single track span. You can see on the drawings here that the signature of Desprez has replaced the signature of Vierendeel. The spans were erected by the well-known company Cockerill. Both bridges were also blown up in May 1940. The double track span was reconstructed just after the war, this one here, but not the single track one. But the canal has been widened twice since then, and also the required level of free height beneath the bridge has increased. Therefore, this old Vierendeel bridge from 1945 had to go, which occurred in January this year, January 2024. Thank you. So presently you may encounter mainly bowstring bridges crossing the canal, either rail or road. Slightly later, at the A-Day of Vierendeel railway bridges in Belgium, the crossing of the Meuse River in Liège. Two parallel bridges, each with 3 spans, 2 tracks, which makes 4 tracks in total. The largest span is slightly shorter than at Mechelen or Herentals. This one also was destroyed, but this time, I would say accidentally. Note the date. It's on the eve of the beginning of the Second World War. In fact, a lightning struck the detonator and spark ignited the explosives, which were already pre-stored in the chambers. During the war, it was partly rebuilt, but after the war, it was replaced by a different kind of steel bridges with plate girders, still in service. Another one crossing the Albert Canal was the longest Vierendeel span ever built, single-tracked, 112 meter. Of course, also destroyed by the Belgian army in 1940. The result is here, rebuilt in 1946. No longer in use since 1992, awaits possible reuse as local crossing for pedestrian, cyclists, or light rail. In Brussels, you can find a second Vierendeel bridge crossing the canal just near the Royal Palace of Laken. This is behind the estate of the Royal Palace of Laken. This bridge replaced in 1942 a swing bridge dating from the early 1900s. Some new Vierendeel bridges were built in Belgium in the 1950s, the last one being this single track crossing near Liège, connecting an industrial site on an island to the rail network. It was restored and repainted quite recently, and here is visited by a party during the International Congress in Construction History that we co-hosted in Brussels in 2018. Maybe you recognize some of the participants there. No, my case study. This concludes the historical part of my presentation, and I finish with a few slides about an expertise in which I was involved. Of course, I was not alone for this expertise. There was a group of 5 people, and in particular, what I will present here comes from the analysis of my esteemed colleague, Professor Philippe van Bogaert, formerly from bridge professor at Ghent University and a bridge designer himself. So I come back to the set of 3 bridges here, crossing the canal at Mechelen. The 2 dating from mid-1950s, behind here, or this one here, or this one here, were recently rehabilitated and restored. When I visited the site in December 2021, the restoration was nearing completion. But the fate of the 1934 bridge, here, this one, or this one, although in heavy daily use for a major line of the network, was under discussion. In early 2020, the owner of the railway infrastructures in Belgium ordered a thorough inspection of that bridge, which had not been maintained and painted for at least 40 years. A thorough inspection beyond routine inspection. Elements of the decks were found to be significantly corroded by rust, and there were also signs of the damages here resulting from the blasting of 1940. But the corrosion problems can be fixed with an overhaul of the deck. But more problematic, more worrying, some very fine cracks were noticed in the vertical posts of both main Vierendeel girders at a limited number of locations, 7, 8 places on both girders. These cracks are very hard to see, often invisible under a layer of paint. They may have escaped previous inspections. But this was worrying enough to limit the traffic on the bridge. Say only 1 track and 40 kilometers maximum per hour maximum. And also commit further studies. A report by a well-known engineering office from Brussels, specialized in controls for the insurance companies, hastily concluded that these were fatigue cracks. Then the owner took the analysis further. First, there was an extensive campaign of material characterization. This is very, very few that I can show because there are pages and pages of different kind of characterization, from which it was confirmed, I suspect, that the steel was a Thomas or bespair and unkilled steel, as usual in Belgium at that time, with very, very low resistance or Sharpie values, even not enough to qualify this steel as S235 by the standards of today at any temperature. And clearly the steel of the plates and of the rolled profiles was not were different. The analysis of the fracture was entrusted to a specialized lab in the Netherlands, but it could not conclude if the cracks were either resulting from fracture, from fatigue, or from the blast loading of May 1940. Other analyses were performed, like the monitoring of the bridge with strain gauges. As you probably know, even with very loads, the magnitude of strains that can be registered are low on railway bridges, but they can be useful to calibrate numerical models. So several numerical models were developed by Tukreel engineers. Tukreel is a specialized civil engineering office with extensive experience of designing railway infrastructures and especially bridges in Belgium for more than 25 years. And at the end of all these studies in 2021, the origins of the cracks was still an unsolved question. And Infrabel, the owner of the infrastructure of railways in Belgium, considered scrapping the bridge and replacing it with a new modern-looking bridge. But the construction of a new bridge requires a permit to be issued, in this case by the city of Mechelen. The city of Mechelen raised in 2021 the question of the heritage value of this bridge. And the city of Mechelen and Infrabel agreed to appoint an independent panel of experts to assess all documents produced in the process and rate the heritage value of the bridge. I was part of that committee, as was my colleague Philip van Bogart. To make it short, the committee found that the bridge had some heritage value, meaning deemed to be listed. The committee also agreed that the most probable cause of cracking was the blast loading of May 1940, and that the cracks had remained unnoticed since then, because there is not only, but a good agreement between the position, the location of the explosives, and therefore the fractured zone, and the positions where the fine cracks were observed. Relatively good correlation. Besides, all the computations indicated that the level of stress at the most critical locations was insufficient to initiate fatigue cracking. Fatigue computations showed that the fatigue life of this bridge after renovation can be extended safely for another 50 years till the 2080s. And this is somehow a testimony to the robustness of the Vierendeel railway bridges, even made with a poor quality steel. Then the owner decided to keep the bridge and restore it as he did for the two adjacent ones. A full renovation of the deck where damages had remained unrepaired since 1940 are still visible. It has just begun recently. Where needed, rivets will be replaced by bolts, because welding is of course impossible on this all steel from the 1930s. Last slide. In the last decade, a bypass was constructed along the existing line to allow the fast traffic to bypass Mechelen station. An additional crossing, a force bridge, was built, and the authors, the designer of that bridge, chose to design a modern steel bridge that somehow mirrored the inversely the shape of the Vierendeels. Hence this portal bridge or frame bridge that now stands in front of the Vierendeel. Thank you very much for your kind attention.
Thank you, Bernard. I think we're all familiar with the Vierendeel name, so that's been a fascinating story and wonderfully told. So, and you brought it right up to modern times. So, on behalf of the Institution of Structural Engineers History Study Group and the London region of the Newcomen Society, thank you for coming over and giving us a fantastic talk, Bernard. Thank you very much. Thank you.
My pleasure.
Do we have any questions from the audience? If you could hold the microphone as close to your mouth as possible.
David Anderson, once of the University of Warwick. I'm interested in the spread of the use of this form of construction in Belgium. Was this a result of Vierendeel's academic position influencing students into his line of thinking?
Yes, that's my opinion. When I showed this slide on a network of influences, clearly he was really a proponent, an aggressive proponent of his system during this whole life. And probably he managed to convince some of his former students in position of power to adopt his system in Belgium, especially in the 1930s. But at that time, I would say there was a lot of research in the 4 universities in Belgium, in the civil engineering department, on different aspects, on these Vierendeel girders. And finally, somehow all the professors were convinced that this was a good system. Anyway, as you all feel, and I suppose as structural engineers, with this shaped form, this parabolic upper chord, under uniform load, this kind of bridge behaves like a bowstring, of course, with no bending in the posts and no bendings in the chords, top or bottom. It's only under variable loading, unsymmetrical loading, that you begin to have some bending stresses. But the case of the uniform loading is the most critical, in fact, for the elements. So that's for the shape, is the parabolic shape.
I think Dr. Orton from Newcomen Society. I'm not really a structural engineer, but I was much taken by the shape of the bridges, which consist of a series of rectangular frames joined by longitudinals. And it's remarkably similar to airships, which consist of a series of rings connected by longitudinals. The main differences are that airships have to be made much lighter and stronger. And of course, excuse me, the overall length might be 3 or 4 times, 5 times the length of a railway bridge. So the calculation methods involved must have been rather similar. And I wondered if you had any information on this.
On the airships? The methods used for the...
On the methods of similarity of methods of calculations. I would have thought they needed to be very similar. And, and in fact, airships did crash, of course, they all crashed, but not usually because of failures in their structure. Not until they started to fly and go around corners, and then the dynamic stresses, which had been ignored, caused them to crash very often.
Yes. So here we enter the story of structural mechanics, structural method of analysis. But quite a long story. But I would say most of the methods that were derived for analyzing these kind of structures were always, let's say, purpose design, adapted to the form, especially typically. It's a lot, because at that time you could only use the force method of analysis of statically indeterminate system. So the question of the choice of the unknowns is paramount, and there is a lot of interaction about what is the best position of the contrafactual forms in this posts. So because at these points we know that the value of C0 is an advantageous position, say that set of unknowns. So believe that the structure of the airships is different group that is different kind of statically determinate structure or channels, and I do not believe that the people involved in this search of the best method, structural analysis of the variables, were also at that time interested in the structural analysis, let's say, of airships. Maybe that's
I'm very right.
sorry.
I'm very right. We have a question on chat from Paul Wood, who asks what advantages were claimed for the design over conventional truss designs.
As I mentioned in my introduction, Vierendeel claimed 3 advantages. One, which is somewhat correct, philosophically from point of view, is that taking into account of recognizing the importance of secondary stresses that are actually present in trusted structures, recognizing that by changing the system from a trusted system with triangles to, let's say, a frame structure with cells, this and taking this into account in the calculation is of course a correct argument from philosophical point of view. Not economical is not correct because the comparison was not correct because the admissible stress was not the same for the design of usual bridges and Vierendeel bridges. And that's isn't typically why in France there were quite never any Vierendeel bridges built because Rizal very early dismissed the idea, saying it was not economical. And it's here when you compare a Roman truss of the same span and a Vierendeel truss, where mostly it seems that you have mostly steel in the Vierendeel truss. But we know today that this may be an advantage regarding the process. And finally, the third argument of Vierendeel, it's more pleasing aesthetically. Okay, that's a choice, that's an optic, can be accepted. Effectively, nowadays, the use of the term Vierendeel is only used in books and structure for architectural students. Never bridge engineer or civil engineer or with civil engineering works will ever speak of Vierendeel type structure today.
I've got another chat question from Werner Lorenz. Wonder at the number of steel bridges that were rebuilt after being blasted. Are they still in use today? And aren't there considerable risks involved in?
So how many steel which have been lasted, which are still in service? So you have the one from 1922, Canada, the first one in Belgium, and I would say running vessels and this running level, which are in fact released after being blasted in place and repaired locally. And so of course this is a sound question for my colleague and friend Vierendeel. I thank him for these questions. Considering all the detailed calculations which have been performed and the test, we believe that it's safe to extend life to this bridge in Mechelen. The tracks are not recent, they are old. They've been there since the beginning. And so the tracks today are much lighter than those of the steam engines from the 1940s. So it's safe to keep this bridge in service for this heritage value. That's what we of course.
Thank you very much for showing your business. And if I would like to ask 3 questions. You mentioned the first load test, which demonstrated like wave fairness and stability, and the later, which is introducing the stiffness. Would you like to share with us your understanding of the brittle fairness of the late 30s and 40s, like in cold winter? And I would be curious to understand how did the design evolve or the detailing changed following these failures. My second question is to ask you about precamber, to know if any precamber is considered during the design of these bridges. And my last question, because as a structural system is not usually as efficient in terms of materials as any other triangulated structure, I just wanted to ask you, what is your personal interest in such a typology?
Okay. Can you quickly remind the first?
Brittle failure. Lessons from
brittle failure. First of all, I have to say that I'm a structural engineer. I'm not a material science engineer. I'm not a metallurgical engineer. I've done a lot of mechanical testing, but really not a specialist of the brittle failure from the material point of view. What I know is that steel produced in Belgium at that time was not of very good quality. Okay, and prone to, due to welding, probably to brittleness by nitrogen. Okay, so after, but of course this was not really known at that time. The understanding of this problem evolved after the war. All this story of the Liberty ships, you know, all this, and the story of the brittleness and the beginning of the fracture mechanics, and improvements were made in the production of steel in Belgium. Also, some better rules for the detailing of the welding connections. So from the late 1950s, welding was again used for welding bridges in Belgium. Second part of the question, recamber. Do you mean just to compensate for the effect of the loading, or an active pre-cambing by pre-stressing? No. No, but they are very stiff, you know. So the deformation under variable loading remains, could be estimated, computed, and tested, and it could be accommodated on the drawing, at the design. I do not know if there is any, typically if the decks were strictly horizontal, or if they had a small initial camber. I cannot answer that. My interest in this, because I would say it's a Belgian subject on history of structural engineering, this story of the Vierendeel. At some time, in all universities, all professors dedicated some part of their research to this question of the Vierendeel structure. So it's part of the DNA of structural engineers in Belgium. That's okay. But more generally, I'm interested in the history of structural engineering and Belgian contributions to structural engineering internationally.
Fred Starr, Newcomen Society. This is a kind of follow-up to the last question. About 6 years ago, the Newcomen Society, on a trip to the Northeast, visited the Billingham Branch Bridge on Teesside, which was the first all-welded steel bridge put up in this country. Now, I think the steel question must be there, because this bridge is now partially out of service, because the haunches of the bridge have been forced in by the embankments on either side, and the center has been lifted up, I think, by about 1 meter. So the whole structure has been distorted to a degree, and there's no sign of cracking there. And we get cold weather in the Northeast too. So I think you can't rule out the steel as well as the welding.
Regarding the Belgian steel, I agree. Probably the main reason for the failure, the cracking occurring in the steel structures, and not only in the Vierendeel structures, other type of bridges, even Warren type, that were welded at that time, exhibited cracking. And this is most probably due to the poor and unadapted quality of the steel for welding. But it was new at that time. It was an experimental, but it was a massive industrial failure in Belgium. But this was, fortunately, I may say, for this, there was the war, and then everybody forgot what happened, and then, but in the industry, they knew, in the industry, for the producers of steel, they knew. But I have to add that the Vierendeel type construction, highly statically indeterminate structure, internally statically indeterminate, is of course prone to built-in stresses arising from the welding, which are less present in typically a Warren type, classical triangular truss, which are more statically determinate, even if a bit statically indeterminate built-in. So it's possible that's an additional cause of the failure of the Vierendeel welded bridges. Road bridge, yes.
Yeah, it's about the welding.
Yeah.
There is a suggestion that with nitrogen steels, nitrogen-bearing steels, that it's not just the stresses in the weld which are a problem. It's the fact that in the heat-affected zone, any nitrogen precipitates which are in the steel decompose, and the nitrogen then goes into the heat-affected zone in a higher concentration. So it makes that heat-affected zone much more susceptible to brittle fracture.
Mm-hmm.
There's a lot of hand-waving about the whole subject of fracture toughness,
Mm-hmm.
but I think that is a very interesting point that I've come across.
Yes, I agree, but as I had to say, I read a bit about this, but I'm not able to fully understand the consequences of that. But I understand what people say about this.
I don't think anybody does.
Okay.
Right, are we all done with the questions? I think so. There's some great questions there and some equally great answers. So I'd just like to say thank you to Bernard, and if we could all show our appreciation in the usual way. Thank you very much.